Hello.
Is very useful because it preserves the value of 2's complement values. So now let's take a quick look at how these immediate values work. So you've seen this before, and now we're going to walk through it now that you know how they're encoded in the instruction. So here's our instruction: add IR6, R0, and 100. Our control is going to tell our ALU to do an add. It's going to tell the register file that it's going to load from register 0, and we're going to take the other value directly from the instruction, 100, but because this is a 16-bit value encoded in our instruction, we're going to have to go and sign extend it to 32 bits. So we sign extend it to 32 bits, do our add, and then we can. Now let's talk about addresses in branches and jumps. So this is how do we use the immediate fields that we just talked about when we're looking at branch not equal, branch equal, and jump instructions. So in MIPS, branch instructions come in two flavors. Branch not equal and branch equal come in the I format, and remember that means there's a 16-bit immediate, and jump comes in the J format, which gives it a 26-bit immediate. But our addresses are 32 bits because we have a 32-bit machine, so we need 32 bits to point to the immediate to get the new instruction address, which is a 32-bit value. So what we do is we treat branch not equal and branch equal as relative offsets. So by being a relative offset, that means we're going to take this 16-bit immediate and we're going to add it to the current program counter. So we're going to add it to the current address of the instruction. Now this is really nice because it means that this can be a positive or negative number, so we can both jump forwards and backwards with branch equal and branch not equal. The jump instruction, we're just going to treat the constant as an absolute value. So we're just going to replace a whole bunch of the values in the current program counter with those bits. Now let's take a look at this. So here's our current 32-bit program counter. So this is the 32-bit value that is the address of the current instruction in memory. And let's see what a branch not equal or branch equal I form program counter. So this is the 32-bit value that is the address of the current instruction in memory. And let's see what a branch not equal or branch equal I format instruction does. So we want to calculate our next 32-bit program counter value, and we've got this 16-bit immediate. Now I told you before we're going to add in this immediate, but we're not just going to add it in, we're also going to sign extend it, because remember we're adding it to a 32-bit value, so we need to sign extend our 16-bit value. We're also going to shift it over by 2 bits, put just 0, 0 in here. And the reason for that is because we know that instructions are word aligned. That is, they're always going to be multiples of 4 in the address, so we're always going to have 0, 0 here. So there's no point to encode the 0, 0s in our immediate, since we know every immediate for a branch is going to have 0, 0, so we shift it over. And this 0, 0 is also going to be in the final program counter value because all instructions are word aligned. Now, in addition to doing this, extending it, shifting it, and adding it, we're also going to add in 4. And this is because we always add 4 to go on to the next instruction. This is just the way the processor is hard-coded to always add 4. So now to calculate the branch instruction, we take the current PC, we add 4 to it, then we add the sign extended, shifted 16-bit immediate, and that gives us our next PC. Now this is a little bit different for the jump instruction. As we said, this jump instruction is an absolute value, so we're just going to replace the bits. So here we take our current 32-bit program counter, we want to generate our next 32-bit PC, take the 26-bit immediate we have in the middle, and we just replace it. So whatever was in the current 32-bit PC just gets replaced with this. And the rest we move down, and of course this last part's always going to be 0 because it's an instruction. So for the branch not equal and branch equal instructions, we're going to add in the immediate. This gives us an offset so we can jump forwards or backwards. And for the jump instruction, we're just going to question, why do we have these 0, 0s at the end of the immediate when we jump and branch? Well, the answer is all of the above. Instructions are word aligned, so we know we'll never have anything other than 0, 0 here at the end. We always jump by full instructions, so there'd be no point in having an immediate value here which let us jump, say, by 3 bytes, so we'd end up in the middle of an instruction. And to convert a 16-bit immediate into a number of instructions, we can just multiply it by 4, because it's 4 bytes per instruction. So having these 0, 0s here both makes sense and allows us to jump further, because now we jump in terms of instructions, not in terms of bytes. So let's take a look at an example of using jump addresses. Here's some code we had before, and we're going to look at the branch and the jump that we have in this code. So here's the branch. We have branch equal R5, R1, and we've got a 3 in here. But the comment over here says we want to go down to line 24. So how does this 3 get us down to instruction number 24? Well, let's take a look. So the original program counter we start at here is 8, because this instruction is at memory address 8. We want to get down to 24. It's the last one down here. So let's see what we end up doing. So the first thing we do is we add 4, because we always add 4. Now we're going to take this 3 into account. So how do we use this 3 when we add it in there? Well, we shift it over by 2 zeros, 2 bits, we put in our 3, and then we sign extend it. So sign extending 3 is going to put a 0 over here. But notice what happens here. When we shift over this 3 by 2 zeros here, that's the same thing as multiplying it by 4. So what we really get here is we get 8 plus 4 plus 12, which does indeed bring us down to address 8. This was the original program counter where the instruction was, plus the 4 that we always add in, plus this 3, but shifted over by 2 bits. Instruction address 20, because our jump is at instruction address 20. And some of these bits are just going to be brought right down, but they're zeros, because they're all zeros up here. And we're going to have zeros over here on the right side, because we always start out with zeros. So we're just going to take this constant and put it down in the middle. So the constant we had from our jump instruction is 2. We're going to put 2 in the middle, and we're going to shift it over by 2 bits, and 2 shifted over by 2 bits is 8. So now we've taken the bits that have this 20 and we just replace them with an 8. So this is going to cause us to jump up to instruction address 8, just as we expected. Now, this looks like a real hassle. And the reality of it is, when you write this code, you just use labels. You can call this here done loop, and you can call this repeat loop, and let the compiler or the assembler figure out exactly what numbers to put in there for you. But it's important for you to understand how to do this so you understand how MIPS is using all of the bits in the instruction fields. So now let's take a look at what kind of branches we have in a program and why MIPS made these trade-offs. So here are 2 different types of programs, integer, these are regular programs such as a web browser, and floating point, these are image processing or scientific programs. And what you see here is the percentage of branches based on how many displacement bits they need. So what you see here is a lot of branches need 1 to 5 bits of displacement. Very, very few branches need more than 11 bits of displacement. So MIP's decision to provide 16 bits of displacement was a pretty good one. So 16 bits is enough for almost everything. Not everything, but almost everything. Now if we look at the type of branches. So what you see here is that for floating point branches, less than and greater than and equal to are very common branch types, but for integer code, the code that most people run, equals and not equals are by far the most common branches. So what MIPS does is it optimizes for this case. That's why we have branch equals and branch not equal instructions. It's for floating point programs where you need to use other comparison operations. So here's a question. How far can you jump with the immediate field in the branch equal, branch not equal instruction? You've seen how it's interpreted, so how far does it get you? Well, it's going to get you minus 2 to the 15th to plus 2 to the 15th minus 1 instructions. So it's going to get you sort of 16 bits of instructions back and forth, not bytes, instructions. And the reason this is in terms of instructions, not bytes, is because we take this immediate value and we shift it over by 2 bits. So instead of having this count directly as bytes, it counts as instructions. So you should note that we're adding in plus 4 here, so it's not exactly that because this limits the range a little bit, but it's a small difference in the overall range. So question, what address is the following instruction going to jump to when the branch is taken? So the instruction is at address 12. So the program counter or address of this instruction is 12. Where are we going to end up when we take the branch? So we're going to end up at address 80. And we can see this because we've got a 16 in here. We know we're going to multiply that by 4. We always add 4, and here's our base PC, so we add them all up and we get 80. Now let's take a look at how you calculate that. So here's our current PC. We started out at address 12 for this instruction. We know we're always going to add in 4. And now we're going to take the constant we have here, this 16. We're going to shift it over 2, which is the same thing as multiplying it by 4. Then we're going to sign extend it. And then we're going to add all this together. So what we get is we get 12 plus 4 plus 16 times 4, which gets us to address 80. So now let's go through a quick summary of what we've talked about with machine code and immediates and encoding. So we've seen that instructions have different encodings in MIPS, and we do this to store different types of data. So we have some instructions that have 3 registers, some that have some immediate fields, some that have bigger immediate fields. In MIPS we have this 3 different types. We have R format, which gives us 3 instructions and no immediate, I format, which gives us 2 instructions and a 16-bit immediate, and J format, which gives us no registers, but gives us a full 26-bit immediate. We've seen that encodings limit how much data we can have, and these are design trade-offs. So MIPS optimizes for the common case, that are these short immediates in 1 instruction, so 16 bits in a single instruction, but it also supports the general case, which are long immediates, but it takes 2 instructions to do that. So the design of MIPS was very clever. They looked at code and they figured out what do you need. Remember the graph we saw about how many jumps you can do with 16 bits of immediate field. And they looked at code and figured out how often do you need long immediates versus short immediates, and discovered that it was best to optimize for short immediates. So they carefully chose this as a trade-off when they designed it, and it turned out to be a pretty good one. So question, how is the 16-bit immediate field in the add-I instruction converted to a 32-bit immediate for adding to the 32-bit register value? Well, the answer is the 16 bits are sign extended. So arithmetic operations have their 16-bit constants or immediate values sign extended. And we can take a look at this. So here I have an example, R3 is 12, and we're going to do an add-I R4, R3 minus 12. So here's R3, it's 32 bits, it's got the value 12 in it. Here's our 16-bit immediate from the instruction, which is minus 12. And you'll notice here that the leftmost bit is a 1, so when we sign extend it, we're going to end up with 1s going all the way across here. So now here's our 32-bit sign extended value. We're going to go ahead and add it, and not surprisingly, 12 plus minus 12 gives us 0. And so this is how the sign extension allows us to do the 32-bit add to get the right value. So another question, what does the I format instruction trade off relative to the R format instruction? Well, it trades off the third register, the shift amount, and the function for a 16-bit immediate. So it's this trade-off right here. So we get rid of this third register that we can specify, we get rid of the shift amount and the function amount, and instead we get a 16-bit immediate. So now you see why we can't have a branch instruction that compares two immediate values, because we'd have to fit in another 16 bits in here somewhere, and we don't have that. Now we're going to talk about how procedures, or function calls, are handled in MIPS. So procedure calls are really important for structured programming. They allow you to avoid repeated code, and they allow you to call functions you didn't write, such as libraries. So let's take a look at an example up here. Here I have some code of A equals 0, I do something to calculate B, and otherwise I do something to calculate C. Now if you look at this code here, you see this is the exact same function, just with different inputs twice. So instead of writing the same function twice, what I want to be able to do is just write a function call. So in this case I'm going to call this update, and what is update going to do? Well, it'll take these two inputs and it will calculate this function. Now how does this work? Well, when I get to this line of code, I'm going to go off and find update. I'm going to go process update. When update is done, it's going to return the value. The value is going to get stored in B, and then I'm going to go and I'm going to continue running after this line. If I get to this update down here, I'm going to do the same thing. I'm going to jump off to update, then I'm going to return to the right place here. So you'll notice that depending on which update I call, I use different inputs, and I return to a different place. So update has to know where to return to, and we've got to make sure we know which inputs to use. So in order to do function calls, we need to be able to put the input data, or the arguments, where the procedure can access it. We need to start the procedure, as we need to jump to the procedure. We need to do the calculation. We need to put the results where the caller, that is the function that called it, can access it. And then finally, we need to return to the right place. So if we're called update from here, we need to return to after this instruction. And if we call update from here, we need to return to after this instruction. So let's take a look at how we do that. So the terminology for this is important to get straight so we know what we're talking about. So the caller calls the procedure. So here main is our caller, and I'm going to call her red in the slides here. So the caller is main. Then the procedure is the thing that's called. It's the callee, which we're going to color here orange. So here we have the callee. So the caller is calling the callee. Now we've got arguments. This is how the caller gives the callee information. So here are the arguments, G and H, and then within the procedure itself, or the callee, you have the arguments as well. So these will be colored blue in the slides. Then the callee returns the result, or the data, back to the caller. Here you can see it returning it. And finally the caller gets it back, and this is green. So we have a caller, which is calling the callee. It gives it arguments, and it returns. So to do the procedure call, we need to be able to do two things. We need to transfer the control to the callee to start the procedure. That's sort of like a jump or a branch. And then when we're done, we need to return to the caller. Again, like a jump or branch, but this jump or branch depends on where you were called from. So somehow we need to remember who called us so we know where to go back to. The way we do this is with the jump and link command. So here's the instruction, jump and link, and then the address. And what this does, it keeps track of the instruction after it, so that when we're done, we can go back to where we started from. So it stores the return address, that is, it stores PC plus 4 in register 31, which has the abbreviation RA for return address. Now when we're done, to go back, we call jump return register address, RA. And this will jump us back to the address in RA. This is why we need to store this value so we can get back. So let's take a look at an example here. Here we've got a program. We've got add. We're going to do some addition. We're going to jump to a procedure, do some more addition. When we get back, the procedure is going to do an addition, and then it's going to jump back. So let's take a look at how this executes. So we execute our first instruction, and we go ahead and update our register file. Then we get to jump and link to my procedure. Now this is going to cause us to jump down here, but it's also going to store the next PC. So here we're on instruction 8, and it's going to store that plus 4, so 12, into register 31. Now we go down to the procedure. We're going to start executing it. We're going to do our addition here, update register 2. We get to jump register, and there should be an RA in here to specify which register, R31. And now we're going to take the value here, 12, which we stored before, and we're going to use that to jump back. So now we're going to jump back here to the instruction right after we called the procedure. So now we jump to this instruction and we do our final calculation. So when we call jump and link, it's going to store the instruction after the one we're currently at in register 31, and when we call jump return with the register, it's going to jump back to the right place. So question, is the code below correct? Well, the answer is no. So when we call jump and link up here, it's already storing the address of the next instruction. So in the procedure, we don't need to go in here and add 4 to it. If we did that, we'd end up going 2 instructions over when we got back, which would probably cause the program to crash. So now let's take a look at a procedure call in more detail. So we're going to use the same example we had before, and we're going to write out the actual code for this. So let's start out and decide where we're going to put our registers. So we've got A, B, G, H, C, K, and M. We have to put them in registers, and here's how we've decided to do it. Register 20, 21, 22 are A, B, and C, and then G, H, K, and M are in 16, 17, 18, and 19. So let's go ahead and write out the code. So here's main. The first thing we're going to do is branch not equal R20 0. So this is our A does not equal 0. We go down to else. If we're going to do the if part, now we're going to call jump and link update. And here we expect the update to use R16 and R17. And when it's done, we expect to put the results in R21, so they'll go into B. Then we skip over the else because we've done the if part. Here's our else, and the else is similar. We're going to call jump and link update, but this time we expect update to use registers 18 and 19 for K and M, and we expect the result in register 22 for C. And that's the end of our code. Now let's take a look at the update procedure here. So here's the code for that, and here's how we're going to do this. We're going to put the arguments A1 and A2 in R4 and R5, and use some temporary variables and put the results in register 2. So here's the code for update. You've seen this before. This is just doing our 2 operations, and then doing the subtraction of the 2 of them, and then when we're done, we return from our procedure call. So here's a question. What's going to happen to the variable A in main when we call update? So to understand this, we want to take a look at who's using what register. So main over here has A and R20, and we're using R20 up here for our comparison. But look what update is doing. Update is using R20 for one of these temporary variables. It actually writes over R20 here when it executes. So the problem here is that since update is going to write over R20, it's going to change the value of A that main had. So if main wants to use A later on in the program, it's now been changed by this update, and that's going to cause a problem. In fact, that's not the only problem. If you look at what else we have here, update expects to have its arguments in R4 and R5, but main expects them to be taken out of R16 and R17 here, or R18 and R19 here. So that's not going to work. If you look over here, update is returning its value in R2, but main expects the results in R21 or 22, depending on where we are. So again, that's not looking too good. And then we have this problem with these temporary registers in R21 for A and B. So writing over these isn't a good thing. So what's going on here? Well, the problem is these 2 pieces of code aren't coordinated. So main and update aren't coordinating which registers they use for what. And this is a real problem. If you want to call someone else's code, say somebody's written a library that allows you to access the internet or draw pictures on the screen, you need to make sure your code is compatible with them, and that means using the right register. So a question about this lack of coordination. Which of the following is not a reason why we need some way, a convention for dealing with procedure calls to coordinate things? Well, the answer here is it's not a problem to know where the procedure is. When we call jump and link, we specify where the procedure is, so we always know where it is. That's not a problem. The other ones are an issue. We need to know where the return value goes. We need to know where the arguments go, and we need to make sure we don't overwrite registers with temporary values. So those are all problems with not having a convention for how we use the register file. So now let's talk about how we go about saving registers and restoring them. And the way we do this is we put them on the stack. And the stack is just a piece of memory, it's a special address in memory where we know that we can save registers. So we talked about needing a convention between callers and callees, and we covered how we need to know where to expect the arguments and results. And we talked about how we could specify particular register files for that. But we also need to make sure we don't overwrite each other's registers. And this is a little bit more tricky. So some of the registers are going to be saved by the callee, and some are saved by the caller. And this is the convention we have. So if the callee uses some of these callee saved registers, then it has to save them. And if the caller uses some of the caller saved registers, then it has to save them. So we divided up who saves what between the callee and the caller. So how do we actually save and restore things? So to save it, we copy a register to memory. And once it's in memory, it won't be overwritten if the callee uses the register. And when we're restoring, we copy a register back from memory to the original register. So we're using this memory location called the stack in order to keep all of these values safe. So why do we need to save and restore in the first place? Well, we saw an example of that where the callee and the caller don't know which registers they use, so they overwrite each other. And in general, this is a real problem. So the callee doesn't know which registers the caller is using because it could be in a different piece of code. Somebody else could have written it. We have this convention that specifies where arguments and results are, but other than that, we have no idea to know which registers which one uses. And the caller doesn't know who's the callee we're using because you could have multiple sub-procedures. So when you call update, update could call special update. And so you could have multiple procedures, so there's no way to know who's using what. So we need this convention which specifies which registers the callee and caller need to save. So how do we save registers? Well, in MIPS, we have a special part of memory called the stack for saving registers. So here's our memory, and you can see we've got some data that we've saved in here. And we've got the special register called the stack pointer, or register 29, which keeps track of this. So here the stack pointer is pointing to the end of the stack. And in MIPS, the stack goes down. So as we put more data on the stack, we're going to move the stack pointer down. So let's take a look at this. Here's our stack pointer before, here's our stack and our stack pointer before a procedure call. Now we're going to call the procedure. So we're going to move the stack pointer down and we're going to save some data onto the stack. We'll move it down again and save some other data, and move it down again and save some other data. So here, for example, we've called a callee, and the callee has decided to save 3 registers on the stack. So it's had to move the stack pointer down 3 words, and then it's stored those 3 registers to the stack. Now, when the procedure is done, it can go and restore those registers by reading the values off the stack, and it will finally move the stack back to where it was before. So during the procedure, we keep all of this safe in memory, and then after the procedure, we're going to return the stack to the way it was before we were called. So here we are. We've now read these off, put them back in the register file, and moved the stack pointer back to where it was. So the stack gives procedures a safe place to store data that doesn't fit in the registers. And each procedure is going to manage its own stack space so they don't interfere. So here we see we've got one. This is the caller's part of the stack, and the callee puts stuff on the end of it. And this works great as long as you return the stack to the way it was before. So here's where the stack was before the procedure was called. During the procedure, it put lots of data on it. But when the procedure was done, it put the stack right back the way it was before it was called. So who saves what? Here's our picture of the register file. And here we've got these red register files, these T or temporary registers. These are caller save. What this means, if the caller uses any of these registers, then the caller has to save them on the stack before it calls. The orange ones, these are callee save. This means if the callee uses any of these registers, then the callee has to save them on the stack before it writes over them. And then it has to restore them from the stack before it returns. So we have callee saved, or S registers for save, and caller saved, or T registers for temporary registers. So how much do we need to move the stack pointer? So the stack pointer address is stored in register 31, which is stack pointer. And how much do we need to decrement it to make space for a register? Well, the answer is we need to decrement it by 4 because each register is 4 bytes wide and each memory address is 1 byte. So if here's our stack pointer, we need to go in and subtract 4 from our stack pointer, and this will put our new stack pointer pointing down at the next location, so we've moved our stack down by 1 entry. So how do we go about actually storing something to the stack? So which one of these is the right code for storing R16 onto the stack? Well, the answer to this is we need to decrement our stack by 4 bytes, enough for 1 item, and then store R16 to that location. So let's take a look here. Here's our stack pointer. We're going to add I minus 4 to the stack pointer. So this is going to cause our stack pointer to move down 1 location. Then we're going to store R16 to where the stack pointer is. So now we've stored R16 onto the stack. How do we restore R16 from the stack? So this is the opposite. Well, here we're going to do pretty much the inverse. We're going to load R16 from where the stack pointer is pointing, and then we're going to add 4 to the stack pointer to put it where it was before. So let's take a look at this. So here's our load word, and here's our stack pointer pointing at R16. We're going to load it into register 16. So now we've restored whatever value we'd saved from before. And then we're going to add 4 to the stack pointer, which is going to move our stack pointer back up to where it was before. So now let's take a look at how this all comes together with nested calls. So here's our main, which is our caller, and main calls B. So now B is a callee from main. But what if B then calls C? So now B is the caller for C and C is the callee. So we've got this nested function here. And then eventually these are going to return. So what happens to the stack in this situation? Well, when we start out, main is going to store some registers on the stack. So here are main's registers stored on the stack, and then it's going to call B. Now when we're in B, B is also going to save some registers on the stack. So here are B's registers on the stack, and it does that before it calls C. And when C executes, C is going to store some registers on the stack. And it's going to go ahead and process this, and then it's going to return the registers back to get back to B, and then it's going to return. So what you see here is that when we get back to B, the stack is exactly the way it was when B had it before it called C. So we've returned the stack to the way it was before. C stored a whole bunch of stuff on the stack, but it took it back and put it back in the register file, and then moved the stack pointer back before it returned. The same thing happens when B returns. So when B returns, we clean up the stack and put it just back the way it was before when we were in main. So what you see here is that the stack grows and shrinks as we call more and more procedures and return from procedures. And each procedure can put data onto the stack, and then it has to make sure it removes data from the stack when it's done. So some machines actually provide stacks as part of their architecture. So the old VAX machines and the Java virtual machine are both stack-based. In MIPS, you have to implement this in software, which is why we're doing all of this work to increment and decrement the stack pointer. Now let's walk through an example of saving some registers. So before we do that, let's ask the question, what registers need to be saved in this example code that we had before? Well, we can take a look at this and we can determine the callee needs to save registers 20 and 21. And let's walk through all the registers that are used here and figure out what we need to do. So registers 4 and 5 and 2, well, those are the return value and the procedure arguments. So we don't need to save those because they're the ones that are going back and forth between the procedure, between the caller and the callee. But let's take a look at these registers, 20, 21, and 22. These are used by the caller, but these are callee saved registers. That means if they're used by the callee needs to save them, but the caller doesn't need to save them. How about these other registers in here, R16 and 17? Well, again, R16 and 17 are callee saved registers. So if the callee uses them, it needs to save them, but the caller doesn't. Same for 18 and 19, callee saved. So the caller doesn't need to save them, but the callee does if it uses them. Now let's go down and take a look at the callee. Well, again, our 4, 5, and 2, these are our return value and procedure argument registers, so we don't need to save those. But registers 20 and 21, these are callee saved. So this means that the callee does have to save and restore these if it uses them, and sure enough, our callee here is using them, so we're going to need to save and restore registers 20 and 21 in the callee. So how do we go about and do that? So here's our update procedure, this is our callee, and what are we going to do? Well, the callee uses registers 20 and 21, and they're callee saved, so we need to save them. And then to do that, we need to increment our stack pointer, that is bring it down, decrement our stack pointer, and we've got two things we need to save, our 20 and 21. So we're going to have to move our stack pointer down by 2 words, or minus 8 bytes, and then we go ahead and save them. So we save our register 20 onto the stack, and register 21 onto the stack. Now we've saved the values of register 20 and 21 from our caller from main before called the update. So main calls update. The first thing we do in update is save the values that main had for registers 20 and 21, and then we do our calculation. And our calculation writes over registers 20 and 21, but that's okay because we saved them. Now when we're done with our calculation, we have to go ahead and restore those registers. So we go ahead and load both of them back. Here we're restoring register 21 from the stack into register 21, from the stack into register 20, and then put our stack pointer back where it is. And we do this so that now when we return, we put registers 21 and 20 back just the way they were when we called main. So now from main's point of view, when it's jumped and linked into the update, registers 20 and 21 are the same as they were beforehand, even though the update procedure used those registers. So let's take a look at this in a little more detail. So first thing we do is we move the stack pointer down. We move it down to give us enough space to put two things on it. Then we save register 20 at stack pointer plus 4 and register 21 at stack pointer plus 0. Then we go ahead and execute our update, which overwrites registers 20 and 21, but that's okay because we saved them on the stack. So we go ahead and restore them to registers 21 and 20 from the stack and put our stack pointer back. Now let's take a look at what happens to the stack and the register file as we do that. So the first thing we're going to do is move the stack pointer down. So here's our stack when we begin. We have some data from the caller on it, and we've got our stack pointer pointing to the end of the stack. Here's our register file. Our register file is filled with data from the caller, and in particular, we're going to look at registers 20 and 21. So the first thing we do is move the stack pointer down, and here we are. We moved it down by 8. So we went from 28 to 20. Now our stack pointer is pointing down here. Now we're going to store registers 20 and 21 to the stack. So to do that, we take the data from register 20 and the data from register 21, and we copy it onto the stack. Now we've saved the values of registers 20 and 21 in case we overwrite them in the register file. Now we go ahead and run update. And update is going to write over registers 20 and 21. So you see here the callee has now written over the data that was in the register file. But it's a good thing we saved that over here onto the stack. Now when we're done with the callee, we need to restore registers 20 and 21 from the stack. So we're going to take the data we saved, which registers 20 and 21 from the caller on the stack, and we're going to put them back into the register file. Once we've done that, we go ahead and move the stack pointer back to where it was, and now what you see here is both the register file and the stack are exactly the same as they were before we called the procedure. So this meant that our procedure didn't corrupt our results here. Now, if you notice what happens here, the procedure is actually going to return its results in register 2, so we get the data back in register 2. Now let's take a look at another example of saving registers, and here we're going to name our registers explicitly to make it easier to remember who saves what. So let's look at some more convenient names for our registers. And you've seen before we have these nice names V0 and V1 for the return values and A0 to A3 for the arguments. We also have a bunch of other helpful names. So these ones here, these T registers, T0 through T9, these are temporary registers. And the idea here is that if the caller uses anything in a temporary register, then it has to save it. The other registers we have here, these S0s, these are saved registers. That means that the callee has to save those. So from the caller's point of view, the saved registers are automatically saved because the callee has to save them, and it's only the temp registers that the caller has to worry about saving. So by having this naming, it makes it easy if you're writing code, if you're writing a caller, to know that you have to save the ones that are in the temporary registers, but if you use these save registers, you don't have to worry about it unless somebody is calling you. So let's take a look at another example. Here's the code for this example. And you can see we start out here setting up our arguments. We're moving different values into our argument registers. Then we're going to call update function. Update function comes down here, and what's it going to do? It's going to do a little bit of work. It's doing this function we saw before, f equals g plus h minus I plus j. You can see we have two temporaries that we use here. We end up with the results in S0, and then at the end, we move S0 to our result register to return the results to the calling procedure. So, what resources does the caller use? Well, if we take a look here, we can see the caller is using these registers up here. So it's using T0, S0, S1, and T0 and T0. It's using these values to store them in the arguments that it's going to have for calling the function. So T0, S0, and S1 is what the caller uses. Now, what resources does the callee use? Well, if we go down here and look at what the callee is doing, we can see the callee writes to T0, T1, and S0. So the callee is writing over T0, T1, and S0. Now here's the interesting question. what does the caller need to save? So of the resources here that the caller is using, what does it need to save? Remember, the caller needs to save anything that's not in the S or saved registers. So the only one here is T0. So the caller is going to have to save T0. Now we can ask the same question about the callee. What does the callee need to save? Well, remember, the callee needs to save anything that's not in the S registers. So, sorry, in the T registers. So it's going to need to save S0. So now we can go ahead and take a look at putting this together. So we know that the caller up here has to save T0. So we move the stack pointer down by 1 and we put T0 on the stack. We call our function. And then when we're done, we're going to go ahead and put it back, restore the value from the stack, and put our stack to where it was. Now what does the callee need to do? Well, we decided the callee needs to save S0. So it's going to do the same thing. Move the stack down by 1, put S0 on the stack, do its work, and then at the end, restore S0 from the stack and put the stack back where it was. So, now question, why does the caller not need to save T2? After all, we're using T2 down here. Well, the answer to this is the caller is writing over T2. It doesn't matter if the callee puts something in T2 because the caller is immediately going to replace it by moving this V0 into T2. So another question, why does the callee not need to save S1? If you look up here, the caller has S1, so why does the callee not need to save S1? Well, the answer here is the callee never writes to S1. It only writes to T0, T1, and S0. So it's never going to write over or corrupt S1, so it doesn't need to save it on the stack and restore it when it's done. So now let's walk through this example in detail and go through what all the lines are doing. So we start out, we notice here from what the caller is doing that it uses T0, S0, and S1. T0 is not saved, so the caller has to save it. And we ask, what about S0 and S1? Well, S0 and S1 are callee saved, so the callee saved, so the caller does not need to save them. So we don't need to worry about S0 and S1 because we know that the callee down here is going to have to save them if it needs to do so. After the call returns, the caller is going to restore T0. And the result is in V0 and we move it to T2. And why didn't we need to save T2? Well, because we overwrite it here. So it doesn't matter if the callee corrupted it because we went ahead and wrote it over. So we didn't care about what was in it. So now the callee, when it runs, finds its arguments in A0 through A3. It uses S0, so it needs to save it. And what about S1? Well, the caller does use S1 up here, but the callee never writes to S1, so we don't need to save it. The results are placed in V0, so the value return register, and then the callee needs to restore S0 that it saved beforehand. So question, who has to save the S and T registers? Well, the callee must save all the S registers, the save registers, and the caller must save all the T registers, temporary registers. But note, you only need to save registers that you use. So the callee here needs to save any of these registers that it uses, but if it doesn't use them, it doesn't need to save them. And the caller needs to save any of these registers that it uses, but of course if it doesn't use them, it doesn't need to save them either. So another question, if a caller uses S0, S1, T0, and T1, how much stack space does it need to use for saving registers before making a procedure call? Well, the answer is 8 bytes here. We need to save two things as the caller. We need to save T0 and T1 because those are both going to be caller saved. So we need to save two things, or 2 times 4 bytes, or 8 bytes. So these are the ones that the caller needs to save. Here's another question. What value should X and Y have in the code below here to make the code correct for saving registers S0 and S4? Well, -8 and 4. So take a look at this. We want to decrement our stack pointer by 8, and then we want to offset this by 4, the second one here. So here's our memory beforehand, here's our stack pointer, and what we want to do is add -8 to the stack pointer. So this is going to move it down by 2 spots. Once we move it down by 2 spots, we store our first value, S0, to the stack pointer, and then our second value needs to get stored to this other spot, which is 4 above the stack pointer. So -8 and 4. So now let's summarize what we've talked about in procedure calls. So when you call a procedure, you need to know where to find their arguments and where to put the results. And we talked about how we have special registers that we agree to for that. You need to be able to save and restore registers to avoid overwriting information that the caller has in the registers. And you need to return the registers to the right positions. We saw we have some results registers and some argument registers. And then we saw the rest of the register divided up into these two chunks here. And one chunk of these was caller saved. That means that the caller is responsible for saving these registers, the temporary registers, if it uses them. And the other chunk was callee save, these save registers. And that means the callee is responsible for saving them if it uses them.
Wait. Yeah, sorry, thanks. We still have time for questions. Mga 15 minutes siguro. So, questions from week 1 videos and week. Question, ano po yung pinagkaiba ng MIPS architecture with Harvard? Is an implementation of a RISC Harvard architecture. So, yung RISC is reduced instruction set computer as opposed to a complex instruction set computer. So, ito yung RISC type. And then, another thing particular about this is yung Harvard architecture, meaning separate yung memory and data. So, hindi dito natin, there's this separation between instruction memory and data memory, CPU, at which allows you to access them simultaneously. So a RISC Harvard architecture. So parang yung ARM, it's another company. So MIPS is a implementation of a certain RISC Harvard architecture. So ngayon may mga bagong lumalabas na mga implementations ng instruction instruction set, like bagong uso yung RISC-V. But the idea here is MIPS is an implementation technology and RISC and Harvard are architectural concepts. Merong transcript ng videos, some have problems with their accents. Sorry. Um, video, if you watch them in YouTube, I think you can turn on closed captioning. And siguro pag may question kayo regarding sa hindi maintindihang words, we can send me the timestamp or send us a timestamp nung sinasabi niya. Baka mayroon hindi clear, but these are the videos coming from native English speakers. So we try to look for videos like that so that it'll be easier for us to. So I think it might have some accent, but it's not too hard, I think. And I think it's understandable. But again, if you have questions regarding what words, uh, maybe you can post it in the forum or send email to us this video with this timestamp, then maybe we can clarify what he was saying. Okay. Yun. What's stopping me from only using Collie save registers in the caller and don't have to save any? What's stopping? Ah, so yung question transaction natin. And naglagay lang tayo ng mga pangalan dun sa mga registers na yun para madaling ma-identify yung groupings, but all those registers could be used interchangeably basta alam mo yung uh, register na ginagamit mo. And yun nga, pag memory, but and then ayaw mong sa memory parati yung transaction mo dahil mas mabagal mag-access ng memory as opposed to a register. Again, balikan natin, no? Physically, yung register, yun yung kasama sa loob ng chip. So any access sa loob nung, naalala niyo yung picture nung pinakita natin last time about yung implementation ng microcontroller, yung register katabi is in the same silicon. And when you talk about a memory, it's normally outside. Now, nagsasalita ako ng ganito in terms of a computer organization framework wherein memory is outside. In the case of a microcontroller, we tried to put also that memory in the same silicon. However, ang difference lang nun, yung flash program memory sa uh, sa microcontroller natin is something that it is a slower technology as opposed to uh, registers na ginagamit sa loob mismo ng microcontroller. Okay. So, hello. Uh, are all MIPS Harvard? Yes. Preference natin dito Stanford. So sila yung nakaisip ng prevalent before is yung yung mga and then ang implementation nun is von Neumann, ibig sabihin memory and they're accessing one lane papunta sa CPU. So people from Stanford like David Patterson sabi nila, invento tayo ng bagong style ng computer and let's call it a Harvard architecture wherein you have two separate lanes for the memory and data memory and the program memory. Doon po sa short quiz, meron po bang question na na-mention 3F? Ah, na-mention yung 3F. Is it really 3F, not 3X? Okay, so questions related sa quiz, well, as of now, pwede niyong i-send muna sa akin and sinulat ko, it's not 3F, I think it was 3B. So, well, anyway, normally 3X is a generic term. Yung X could represent ports A, B, C, D, E, and F. So, um, right now we're trying to discuss some changes in the way that we're setting up the quiz, especially the lines right now. Although we are allowed for multiple quiz, the deadline is on December and parang hindi na rin medyo pwedeng ibigay agad lahat yung sagot in that setup. So we're trying to devise a way, maybe moving than what we have mentioned since biglang hindi tayo makapag-discuss ng the end of the semester. Okay. Other questions? So, I think take this opportunity na rin. Last time may mga nagtanong bakit yung mga yung sa memory map, physical memory map, merong 1 MB na special function register na lagpas dun sa size nung 512 kilobytes ng program flash. And so, idea here yung special function registers are part of memory, program flash memory and the data RAM memory. So it's a separate memory na na-access ng CPU. Now, again, just to remind us, no, yung week 1, we talked about microcontrollers and lahat ng sa paligid, yung elements ng microcontroller, tapos meron kang sa gitna nun is a heart of a MIPS CPU core or a CPU core, kahit ano pang generic. But for our case, it's a MIPS CPU core. Now, ngayon, yung week week 2 na to, nag-focus tayo what's inside the memory core, which is essentially yung MIPS microprocessor, and it is executing these instructions. So pumasok tayo ngayon sa loob ng microprocessor, pero sa next meetings hanggang sa meeting processor, magsisimula ulit tayo bumalik sa loob ng MIPS. Then paano na-execute itong mga instructions na to, ano yung circuits, ano yung mga dinadaanan niyang circuits para ma-implement yung mga instructions na na-mention natin. Okay, so maybe a few minutes more. Ano pang question? With regards sa book na I hope na access niyo naman or na download niyo na yung reference natin on PIC 32. Tapos I also added some materials na pwede niyo na kailangan niyo basahin doon sa week 2 na module. So may ilang materials doon. It's a complete summary of the instructions. So makikita natin sa lecture natin dito, pinakita natin yung mga instructions na add, subtract, add immediate, tapos yung mga branch, link, and jump. Now, marami pang ilang logical discuss in detail dito. So makikita niyo yung summary of how those things are executed dun sa summary box ng mga instructions dun sa text, sa readings na nilagay natin. So maraming links doon, and then try to read those links to get a more complete idea ng mga instructions. Now, medyo ginawa natin itong part na to dahil halos sa time na to ng 158, you will be doing the programming of the microcontroller, and you will be using the assembly language, and medyo in time tayo, sakto tayo dun sa kailangan natin to write some codes, at least naintindihan na. Okay. So ilan tayo ngayon? Medyo konti lang tayo ngayon, 20. So no need to get the 300 account from UP. Hindi ko pa rin naayos yung UP account ko. But I think we're still good with the 100 students. Ano pa? Oops. Well, last 5 minutes clock ko. And can dismiss early if kung wala nang tanong. So last call for some questions, or baka may gusto magtaas ng kamay at magsalita at video screen. Okay, it seems na wala nang question. So again, we have lahat, maraming send Ovle forum or sa piazza. So maraming avenues to discuss. Okay? So I guess we're gonna end the watch session here, and then there will be another one, I think, on may isang Tuesday, tas may isang Friday. Hopefully it covers lots of people naman na hindi magko-conflict sa mga class nila. Okay, so if there are no more questions, then I'd like to end this session. So thank you.